Today, in this session, I'm going to explain another important experiment in digital communication lab, that is binary cyclic code or simply cyclic codes. Here, we'll understand both encoding and decoding as well. So before understanding the cyclic code experiment, so you should need some theoretical knowledge about what is cyclic code and why it is used. So before starting the experiment, first I will explain about what is the cyclic code and theoretical concepts as well as design concepts also. How do you design encoder and decoder? Everything I will explain. After that, we will see the experimental analysis. Now, let us understand the basic block diagram for digital communication system. There are different elements are there in the entire communication system. Out of this, so there is a two types of coding techniques are there, which applies after the source, as source encoder is one and channel encoder is another. Source encoder just give the or just produce the some group of bits for each and every symbol that is generated from the source. That means simply it converts some symbols to bits. So we have some number of bits at the output of this encoder. So the purpose of channel encoder is this purpose, this particular block, that is channel encoder. This is especially used for error detection and correction in the entire digital communication system while we are receiving the data. So there are different types of channel coding techniques for the purpose of error detection and correction. One of them is linear block code and another one is cyclic code. So today we are going to discuss about cyclic code. Here, how the error and detected and how this error is corrected. This is done in the channel encoder by adding some extra bits to the original bit sequence which is coming from this source encoder. For example, this is the source encoder output having 5 bits. So some 3 bits, that is extra 3 bits, are added to this one, so that total bits are 8. So these extra bits are known as parity bits, which are used in order to detect and correct errors. But of course, this is unnecessary or redundant information. Anyway, those parity bits are eliminated at the channel decoder. So in this session, we will discuss both channel encoder as a cyclic code. So cyclic code encoder as well as cyclic code decoder we are going to observe. Now, let us see the basic definition of what is a cyclic code. So it is one of the channel coding method like linear block code, which is used for error detection and correction. A binary code is said to be a cyclic code if it exhibits two such properties. That means if any code is satisfying these two properties, then we can say that that is a cyclic code. One is linearity, another one is cyclic property. So what is the meaning of linearity means? For example, we have some set of codes like this. This is one code word which is generated from the encoder. Like that, we have some 10 such codes depending on the combinations of the input. So linear property means the sum of any two code words is also another code word in that list. Then we can say that that code is satisfying linearly. Similarly, the cyclic shift of this code word, if we shift this bits cyclically, then the output is also another code word in that list. Then we can say that it is satisfying the cyclic property. So if any code is satisfying both these properties, we can say that that is a cyclic code. So these two are the fundamental properties of cyclic code. And what is the advantage of cyclic code means? By using cyclic code, it is very easy to encode data because it has a mathematical structure. Mathematical structure means in this cyclic code, all the code words are represented with polynomial equations. So that means every representation, not in terms of bits, so every representation is given in the form of mathematical equations or polynomial equations. So that's why if anything is represented perfectly mathematically, then the practical design is very easy. And what are the types of cyclic codes? Here we have two types: systematic cyclic code and non-systematic cyclic code. So as you know that cyclic code is one of the channel coding method, just adding parity bits to the original bit sequence. So if we add parity bits exactly after the message bits, then that is called as systematic code. So for example, here M is the message bits, P is the parity bits. So after these 4 message bits only, the parity bits are added in a systematic way. So that's why it is called as systematic cyclic code. If those three parity bits are added in between these message bits, then that is called as non-systematic cyclic code. Now let us see the mathematical representation of systematic and non-systematic cyclic code. For a non-systematic cyclic code, the output code word or a code polynomial is obtained by simply multiplication of the message polynomial and generator polynomial. As we see in the linear block code, similar equation, similar formula is there, like multiplication of message matrix as well as generator matrix. So instead of matrix, here we have equations, polynomial representations. In next slide, we'll see what is the meaning of these polynomial representations. Similarly, we have another formula for systematic cyclic code. That is, the code polynomial is equal to x power n minus k in term of x plus remainder of the same term, that is x power n minus k in term of x by g of x, where g of x is the generator polynomial. So this generator polynomial must be given by the designer itself. So we should know this in order to calculate this code polynomial. Of course, we can change the message bits as per the given data. So here n comma k means every cyclic code is represented by n comma k cyclic code, where n is the number of bits in the final code word. For example, here 7 bits are there, so n equal to 7 here. Similarly, k is the number of bits in the message, data, that is 1101. So 4 bits are there. For example, for this particular type, we can say that it is a 7, 4 cyclic code. So based on n comma k values, we need to substitute here. Okay. So in general, practical analysis, systematic cyclic codes are generally used. So in our experiment also, we have used systematic cyclic code, and we'll see that. So these are the standard polynomial equations for message and generator polynomials. For example, for a n comma k cyclic code, the message polynomial is represented like this, like a mk minus 1 into x power k minus 1, and so on. Don't worry about these notations. So you can simply observe from the example. For example, if it is n 7, 4 cyclic code where n is 7, k equal to 4. So here k minus 1 is equal to 3, right? So k equal to 4, so k minus 1 is equal to 3. So the maximum power start from x cube, and these are nothing but the coefficients of these values. That means what are the values are there, those must be substituted here. So 1 into x cube, so 0 into x square, so 1 into x, so 1 into 1. Finally, x cube plus x plus 1. Okay. So whatever the component is there, that means the value is 1. So if x square term is not there, means so we need to substitute that as 0. Like that, we can easily convert bits into equation or equation into bits. In either way, you should be able to write. Similarly, this is the standard form of generator polynomial. That is starting from 1 plus g1 into x plus g2 into x square and so on, plus last one is x power n minus k. Similarly, if you observe it is a 7, 4 cyclic code, then the first term must be 1 and the last term must be n minus k means 3. 7 minus 4, that is 3. So first term 1, last term is 3. So 1 plus x cube. In between, there will be some generator coefficients. Okay, we'll see what are these generator coefficients. So as an example, this is the general representation of generator polynomial. That is something like 1 plus x cube. But if we compare this with the standard notation, so 1 is there, x term is there, so g1 is there, but x square term is not there. But finally, x power n minus k, that is x cube term is there. So totally we should have two coefficients, but the one of the coefficient is 1 and another one is 0. So only g1 term component is there, so g2 is equal to 0 because x square term is not there. Okay, so based on that, we need to identify the coefficients from this and from this also. So these are the standard representations of generator polynomial and basis polynomial. Okay, so we are going to use this in next session, next discussions. Okay, so this is the general example how to calculate the code polynomial by using a systematic cyclic code, given that it is a generator polynomial and given that there is a message bits, only message bits are given, so we need to convert the bits into equation. As I said earlier, from these notations, you can directly write the equation for m of x is equal to So since the number of bits are 4, so we need to start from x power a minus 1, so x cube. So 1 into x cube plus 1 into x square plus 1 into x plus 0 into 1, so no component. This is the equation for m of x directly. So I am taking the formula representation directly, that is code polynomial can be obtained by using this formula. Substitute this formula directly, that is x power n minus k into m of x plus remainder of the same term by g of x. So x power n minus k, that is x cube into m of x plus remainder of the same term by g of x. So we need to find the remainder of this division. So that find the remainder of the division separately like this. So this one is divided by this x power 6 plus x power 5 plus x power 4. This is the multiplication. So when you multiply the x cube, this is the x cube is multiplied with x cube, x power 6, x cube is multiplied with x power 4, x cube divided by, sorry. After this, the remainder is, since we know that in cyclic code and block codes, the summation must be considered as a XOR operation. So same values are going to be XOR so that output will be 0. So that's why same values are getting cancelled here. X power 6 cancel, x power 4 cancel. So only the term is x power 5 plus x power 3. This is the remainder. So next division is multiply with x square. So this is the term. By cancelling this, finally we have a remainder as x square. So that component must be added after this. So x square is added. Now, similar to the message polynomial representation, we can also find the code polynomial from this code word. So this is what the code polynomial. From this code polynomial equation, we should be able to write the what is the bit sequence. So since we know that output code word contains 7 bits, so we need to start from the component x power 6 to 1. Okay, so 1 into x power 6, 1 into x power 5, 1 into x power 4, 0 into x cube, 1 into x square, 0 into x, 0 into 1. So finally this one, x power 6 plus x power 5 plus x power 4 plus x square. This must be first written like this. Based on these coefficients, you can directly write the bit sequence. So 1 1 1 0 1 0 0 like this. Okay. Similarly, we have another example. So this example is taken from the experiment. So if you are using hardware kit, then this is the example we generally taken in the experimental analysis. So consider the input as 0 1 0 1, and theoretically first calculate the code polynomial or a code word by using this equation. So same formula is applied. Okay, first we need to convert this into equation like. So since we know that it is 7, 4 cyclic code, so 4 bits are there. Start from x cube. So 0 into x cube, 1 into x square, 0 into x, 1 into 1. Finally, it is x square plus 1. Only this is the remaining component. So m of x is this one. Substituting m of x and g of x in the systematic cyclic code polynomial equation, find the remainder. So remainder is x square. We add this here. Again, represent this in the standard notations starting from x power 6. Okay. So no x power 6 component. So 0 into x power 6 plus 1 into x power 5. No x power 4 component. So 0 into x power 4. 1 into x cube. 1 into x square. So no x, no 1. So no other component. So 0 into x plus 0 into 1. So the remainder, if you write all the coefficients one after the other, that will give you the code word or output bits directly. So 0 1 0 1 1 0 0. So this is what the systematic code word from the cyclic encoder. You can clearly observe this is the systematic code because this is the message bits, that is 0 1 0 1. Only after the message bits the parity bits are added systematically, that is 1 0 0. So if anybody asks what are the parity bits in this code word, so 1 0 0 are the parity bits. What are the message bits? These 4 message bits are the message. Okay, finally how many bits are there in the code word? 7 bits. 1 2 3 4 5 6 7. So since that's why it is called as 7, 4 cyclic code, where 7 is the number of bits in the final code word and 4 is the number of bits in the message, and n minus k, that is equal to 7 minus 4, which is equal to 3. So that value represents the number of parity bits in the code word. How many parity bits are there? 3 parity bits. So that is calculated by simply n minus k. Okay. So this is the theoretical analysis you must do while doing the laboratory, or maybe which is very useful in the theoretical class also. This is how we can obtain the code word by using the polynomial equation or a formula for systematic cyclic, right? Next, going to the design concept. How do you design the encoder and decoder for a cyclic code? Okay, let us see in a very brief way. Find the code word for a given message, same message, by using the encoder diagram for a cyclic. Okay, that means of course you can find out the code word by using this formula, and similarly the same output can be obtained by using the encoder diagram also. This is another way, because practically only the shift register diagrams are there. So these are the designer diagrams. The same diagrams are same shift register circuit which is going to be implemented in practical. Okay, so how to obtain the code word by using this diagram? So let us see encoder diagram. This is the design of the encoder. So in order to draw this diagram, the first step is identify the number of registers here. How to identify the number of registers? The number of registers are identified based on the number of parity bits. So how many parity bits are there? Without knowing this, you can easily find out that for a 7,4 cyclic code, the number of parity bits are 3. So if 3 parity bits are there, we need to draw 3 registers first. So first draw these 3 square diagrams as R1, R2, R0, R1, R2. Then complete the remaining diagram. So that is the first step, identify number of registers. Next, from the output of the last register, we need to make an XOR operation with the message bits. So these are the message bits. So these must be XOR operated with output of the last register, and that output must be connected as the feedback to all the remaining registers. Okay, and also in between two registers there must be an XOR operation. So this is the second step. Assume that there is an XOR operation between the any two registers, but this XOR operation will depend on the feedback connection coming from this output. Okay, so how to identify whether there should be a feedback connection or not? This depends on the coefficients of the generator polynomial. So directly go to the generator polynomial equation, that is 1 plus x plus x cube, and identify number of coefficients by comparing with the standard notations. So here we know that only 2 coefficients are there, g1 and g2, since the last value is x cube. So 1 plus x into 1, that is g1 is equal to 1. So 0 into x square, so g2 is equal to 0, plus x cube, that is the last term. So we know that g1 is equal to 1 and g2 is equal to 0. So these are the feedback connections from this output, as which the number of feedback connections depend on the number of coefficients. Since we have 2 coefficients, so there should be 2 feedback connections. If any of the coefficient value is 0, so there should be open circuit. So no connection must be there. If there is a coefficient which is equal to 1, then we should connect a short circuit point. That's why even though we have G2 is equal to 0, there is no connection because it is open. So that's why there is no XOR operation also. Okay. For example, if the generator polynomial is 1 plus x square plus x cube, if it is different, the coefficients values are different. So of course G1 is 0, G2 equal to 1 here in this case. So here there is no connection. Here there should be a connection with XOR. So like that, we need to make an XOR connections between the registers. So that is the second step. Okay. So I'm repeating again. First step is draw the number of registers first, and second step is connect the message bits to the XOR operation at the output of the last register, and connect this feedback to the first register first. So this is the fixed. And in between, depending on the number of coefficients, we need to connect the feedback elements with the XOR operation in between the registers. So here only one coefficient is there, that is equal to 1. Remaining are zeros. So we have only one connection. Next. Here the input bits, that is M. Based on this tabular notation, we can directly obtain the output code word. Okay. So let us see how it is. So these are the shift register contents before shifting operation, and these are the shift register contents after the shift operations. Okay, like R0, R1, R2. So let us assume initially all the zeros are there in the shift register contents. So whenever we are giving the input, automatically these values are shifted right, and again they will be repeated and shift right, and so on like that. That's why it is called as shift register circuit. First input is 0. So because what is the input here? 0, 1, 0, 1. First input is 0. If the input is 0 coming here, so that is making an XOR operation with R2. So R2 XOR with M, that is coming feedback to these elements. So the next values of these shift register contents are represented with R0 dash, R1 dash, R2 dash. So where R0 dash is, the next value is obtained from this feedback connection. So that is coming from this formula. So R2 XOR with M. Next, R1 dash is coming from the XOR operation of these two. This one is R2 XOR with M, and this one is R1. So R2 XOR with M, XOR with R0. Next, R2 dash, the next value of R2 dash is nothing but the previous value of this one. So R2 is equal to R1. So previous value of R1, which is same as the next value of R2, that is R2 dash. Okay. So the table goes like this. Initial values are zeros. So based on this, substitute the formulas. So R0 dash is equal to M XOR with R2. So M XOR with R2, that is 0. Next, R1 dash is equal to M XOR with R2 XOR with R0. All the zeros. So R2 dash is equal to R1, 0. So again, repeat the same. Continue this 0, 0, 0 as the present value now when the input is 1. So next input is 1. Consider the present values of the shift register contents are same values as previous. So repeat the same here, and based on these values, find out R0, R1, R2 dash as 1, 1, 0. Okay, because R0 dash is M XOR with R2, M XOR with R2, that is 1 XOR with 0, that is 1. R1 dash is 1 XOR with 0, XOR with 0, that is again 1. R2 dash is equal to R1, so 0. So repeat this process until the last value of the input. So finally we get this. This is the final contents of the shift registers. So these values are considered as the parity bits, that is P1, P2, P3, where P1 is the least significant bit and P3 is the most significant bit. So while writing, you should start from here and you should end here. Okay. So the corresponding encoder output is, for a systematic cyclic code, is first we need to write the message bits, that is 0, 1, 0, 1, 0, 1, 0, 1, and then you should write the parity bits starting from MSB to LSB. So 1, 0, 0. So 1, 0, 0. You can clearly observe this is the code word from the diagram and this is the code word from the equation formulas. Both are same. Similarly, what is the decoding process? So the decoding operation and error correction and detection is done based on the concept of syndrome decoding or syndrome calculator, which is already explained in the linear block code. But of course, what is there in this particular cyclic code, once again we'll see. Okay. For example, we need to detect and correct errors in the received code word. So the received code word is given as 1101100. So we can clearly observe in this received code word the first bit is in error because this is the original code word 0101100. So 0 is replaced with 1 here. So we know that because we are giving as an example, so there is a error in the first bit. But without knowing that information, this syndrome calculator and decoding circuit should identify that there is an error in the first bit. Okay, let us see how it is identified and how it is calculated. So in order to identify the syndrome, in order to identify the error detection and correction, first we need to calculate the syndrome vector as it is as like in the linear block code. So for the calculation of the syndrome vector, here we have a similar diagram as is in the encoder. So number of syndrome registers are again same as the number of parity bits. So again 3. Okay, but the difference between this diagram and this diagram is, instead of having a XOR operation at the output side, so there is an XOR operation at the input side in the syndrome calculator. That is only the difference. There is nothing difference here. You can clearly observe this XOR operation is replaced here. And of course, in the encoder side, message bits are making an XOR operation with this output. But in the syndrome calculator, the received vector is making an XOR operation with this feedback output. Okay. So the last register content is getting feedback connection to this here. In between, the number of feedback connections are depending again based on the generator coefficients. Again, same generator polynomial is there. So G1 is equal to 1, G2 is equal to 0. There is a connection, so there is no connection. So similar circuit is there. Similar table is there. Okay. Similarly, here this is the received bits starting from 110, 1100, 1 by 1. We are given register content before shift, register contents after shift. So here some formulas are changed. What is that? S0, S1, S2 here, and next values are S0 dash, S1 dash, S2 dash. So what is S0 dash? How it is getting? S0 dash, the next value is obtained by making an XOR operation with received vector and this feedback element. What is this feedback element? That is nothing but S2. So Y XOR with S2. Next S1 dash is nothing but how it is getting XOR operation of these two. XOR operation of S0 and XOR operation of again S2. So S0 XOR with S2. Next S2 is nothing but next value of S2 is nothing but S2. So S2 dash is equal to S2. So based on these formulas, initially assuming all these register contents are 0, 0, 0. S2. So initial value is 1. So 1 XOR with S2, that is 1 XOR with 0, that is 1. Next S0 XOR with S2, that is 0. Next S2 dash is equal to S1. So S1 is 0. So 110 is repeated here as the present value. Based on these values calculated from these formulas. So this cycle will be repeated until the last value of the received vector. And finally we have obtained that the syndrome vector is 1, 0, 1. So finally S is equal to 1, 0, 1. As we know that from the syndrome analysis, syndrome decoding method, if S is equal to 0, that means all zeros, then we can say that there is no errors. Okay, there is no errors. But if S is not equal to 0, having some values, definitely there is an error. This is the first identification. So error detection is done. It detected that there is an error. Next, how to identify where the exactly an error? In which bit position, either first bit position or second bit position, that is identified by from this particular process, decoding process. What is this decoding process? From the received code word, the first step is from this received code word, we need to identify the syndrome vector from the syndrome calculator. So the syndrome vector is already calculated at 101. This is what the 101. So this syndrome calculator must be compared in the lookup table. This is what the lookup table. For this lookup table, for every value of syndrome, there will be some error pattern. This is a predefined table. Okay, this is given by the designer. And of course, we can also calculate all these values and we can summarize this also. But anyway, we can use this table as a lookup table. So if the syndrome value is 0, 1, 1, then definitely there is an error in the third bit position. For example, if the syndrome value is 0, 1, 0, so there is an error in the sixth bit position. Like that, error bit position can be easily obtained from this error pattern. But for our example, 101. So this is what 101. So 101 is there, which is matched to the first bit position. So we can easily detect that error is there in the first bit position, because we already given there is an error in the first bit position. So without knowing that information, this decoder circuit identify that there is an error in the first bit position. So how to correct that? Just we need to reverse this bit. So to reverse that bit, make an XOR operation with received code vector and error pattern. This one and this one. Okay. So here, what is the error pattern here? What is the error pattern here? Sorry, this is not the error pattern. What is the error pattern? This one. That is 1. First bit is only 1 and remaining all bits are zeros. Just by making an XOR operation, simply 1 XOR with 1 becomes 0 here, remaining as is will come. So this is what the decoded data, and finally you can clearly observe that this is the error is corrected. Okay, and from this first 4 bits are message bits and next 3 bits are parity bits, because we know that it is a systematic cyclic code. So just by separating the parity bits, we can directly obtain the message bits, the 4 message bits directly, 0 1 0 1, which is the number 5 as a decimal representation. Okay, now this is what the circuit connection. Everything is explained here, only just you need to observe what is the output coming and what is the input we are giving. That is, the experimental analysis is very simple, but understanding of cyclic code and what is happening is more important. That's why I have explained more in detail up to now. But from this, you can clearly observe in a very brief way. This is what the hardware kit for cyclic code. You can clearly observe this is what the encoder diagram. This encoder diagram having 3 registers, 1 XOR connection. Here there is no XOR connection. You can clearly observe this is exactly same as this one. Okay. Similarly, this is what the syndrome calculator. So 3 registers S0, S1, S2, 1 XOR operation, no XOR operation. Initially we have XOR operation here, and in the encoder side, the last one is the XOR operation. So same diagrams. Okay. You need to compare this. Okay. Now you need to give an input from this data. So from this DCD display, you can give as a number, for example, here 0, here 5. So 0, 5 is given. That number 5 means what is the binary representation for 5? That is 0, 1, 0, 1, 0, 1. So that's why I have taken this as 0, 1, 0, 1 as an example. So to match that example, we need to take this as a number 5, 0 and 5. Okay. Now, as per the connections, we need to connect this is what the connection diagram. So this data, decimal data must be given as input to this encoder. Now this is what the encoder output, that is the code word which is getting here. And in order to synchronize these circuits, some clock signals must be connected. So taken 16 kHz clock, and data clock and code clock are 2 separate clocks are there. Whenever you have a data clock, you must connect this, and whenever you have a code clock, we need to connect this. Similarly, in the decoding side also we have data clock and code clock, so those must be connected as usual. So this is what the code word. So if you don't give any error, so directly that is given to the decoder, so that will be decoded as a again 0101. So same number 5 is displayed here, but without error. But if you want to give an error and try to identify what is that error and how to detect and correct errors, then connect this final encoded output here as a serial to parallel converter. So convert this data to parallel connections. Now, if you want to give an error in the first bit position, already in the example I have given the error in the first bit position. So if you want to change the first bit value, then what we need to do is connect this output to here, and instead of connecting all these directly, if you connect all these directly here, then there is no error. So if you want to make an error, the first bit is connected to NOT gate and the output is again connected to here. So automatically the bit is going to be changed. The remaining are as it is, right? So this is the code word with error. Now we are getting a code word with first bit error. Now that is given to the syndrome calculator, and this syndrome calculator will calculate the syndrome value. Based on the syndrome value and lookup table, this error pattern is making an XOR operation with the received code vector. Finally, the corrected code word, like this will be coming at the output. Okay, this is what the corrected code word. So this decoder simply separate here. Okay. Now, as a sample values, you can look at this. This is what the encoder output, which is what the code word, that is 0101 100. What we have already calculated theoretically The same code sequence is obtained, but this will be repeated like this. Similarly, code word with error, that is the first bit error, automatically you can clearly observe this first bit is going to be changed to 1. So there is an error in the first bit. So that error is automatically corrected. You should see in the experiment. Okay. So you should carefully observe in the CRO as a bit sequence like this: 0, 1, 0, 1, 1, and after that zeros. Similarly, 1, 1, 0, 1, 1, 0, 0, and so on. Okay. The same what we have already analyzed in the theoretically, that those must be observed in the practical CRO, and you should verify with the theoretical values. Okay. So as experimental analysis, don't confuse with these connections. So whatever I have said already with the hardware kit, the same connections are given. So data clocks are connected, encoder output is connected, all these parallel data values are connected to here, except there is a first bit position which is connected to the NOT gate. And the code word output is connected here to the syndrome calculator and then to the decoder. Okay, don't worry about this wires, too many wires. Connections are very simple. Okay, connections are very simple. Just observe what is the input you are giving, that is 0, 5, that is number 5 as a 0, 1, 0, 1, and that is given to the input of the cyclic encoder. Okay, just observe the connections. What is the connections? This is what the code word we are getting, and after properly connecting this, the decoded output also should be number 5. Here also number 5, here also the same digit must come. Okay, even though there is an error we are giving, so that error is automatically detected and corrected. Finally, the same data is coming. For example, if you want to observe what is the code word, then connect that signal to the CRO probe, then you can clearly observe this is what the output. So from this output, you need to observe what is the code word. Then this is connected to the serial to parallel converter, and first bit is given as an error. Then observe the code word with error. Observe the code word with error. So that is what the experimental analysis of cyclic encoder and decoder. These are what the observations. You need to observe the each and everything in the CRO, and you need to compare with the theoretical and practical values, right? So doing the experiment is very simple, but analyzing everything is a difficult part. Okay, so that's it for the class. Thank you very much.